Welcome, Nitin sir.
Hello, sir.
Hello. 1 second.
Yeah, better now.
Welcome, Nitin sir.
Hello, sir. Good afternoon.
Good afternoon, sir.
So I guess when the video is on, there is a slight delay due to the bandwidth being limited.
Okay, no issue.
The voice,
It's work fine, sir. You are looking great. No issue.
yeah, I'm good. So let me just share the slide set. Okay. Is my slide visible?
Yeah, it's coming, sir. It's visible. It's visible.
Oh, okay.
Okay. No issue. No issue. Okay, so
So
we'll
I'll
start
keep
here.
it.
Yeah.
I'll keep it in copy. Is
You
it visible now?
right now it's not visible. Like it's not like you can make it full screen now. Then it will be more visible
Okay.
because we are making live on YouTube now. So just make
Is it
full. Yeah, it is fine. It is fine. It is fine now. Yeah, it is fine.
okay?
You can hide this. There's a link is coming. Stop sharing. Yeah, fine. Now it is good. That is good.
Okay.
उसको लाइव नहीं करना है इस लाइव
Just let me know, sir, when we are good to go.
tell you, sir, within 5 minutes we'll start. By 3 we'll start.
Okay, perfect.
वो आ रहा हो ना स्क्रीन
So how is the workshop going on, sir, for the last 2 days?
Thanks, sir. We already had finished 2 sessions today, and today also we finished 2 sessions. So we are entering into 5th session. So
Perfect. So how is the response coming in? The people are
Very
joining in, and then
Yeah, they're coming like around on an average 700, 800 responses are coming. That feedback we are taking.
perfect. So I was going through the website, and I could see there was a lot of seminars which are going on with an IT center
Yeah,
right now.
yeah. So many, so many.
Yeah, a lot of workshops. So I have also set up something as an hardware to just uh, give
Very good, sir.
detailed
Excellent.
something about the actual setup that's being required.
Okay, great, sir. एक मिनट.
So more of the people are joining through Google
YouTube,
Meet.
YouTube,
Oh,
YouTube, YouTube.
they're majorly
For
joining through YouTube.
No, actually, for participants, we shared only the YouTube link. Okay, for only internal parts like internal faculties and coordinators are in the Google Meet
Oh,
and
okay. So
experts.
that absolutely. Otherwise, the
Yeah.
Google Meet will crash if
Yes.
there's
So they,
more than maybe 200 participants. Then
yeah.
that might give you a challenge. Yeah.
So Nitin, you can do one thing. You can share your the screen. Okay, the
Okay.
first screen. Okay, then we are going to start now.
Am I good? Are you able to see the first screen, sir?
Yes.
Okay.
Pin, pin karo. Just pin it. So, welcome back in the fifth session of today's. Sound is coming. Sound is coming. No, 1 second. Okay, so we are going to start our afternoon session. Okay, so among us, we are having an expert from Tektronix, Mr. Nitin Nigam. So it's my sir, welcome, sir, for an STTP, sir, Mr. Nitin Nigam. Sir, some noises are coming from your side, or uh,
I Is it okay?
some? Yes, it is fine. Some noises are coming. Uh,
Okay.
it is fine. It is fine, sir. Sir, it is
Okay.
fine. Okay. So, Mr. Nitin Nigam is an application engineer with Tektronix and working with Tektronix for last 10 years. He had been actively involved with power electronics design industry in their test and measurement phase. He presented at various national and international forums and seminars on power solutions and actively involved with multiple IITs and NITs in the country for test solution consultancy. Today, he is going to deliver a talk on understanding the key critical measurement challenges and testing of next generation power electronics based SiC and GaN based devices. So, we'll welcome again Mr. Nitin Nigam to deliver a talk. Sir, please take the session, sir.
Hi. Good afternoon. Thank you so much, sir, for inviting me for this particular session. Welcome, everyone, and thanks for joining this session, which is based on the testing and measurement challenges of wideband test devices. I hope everybody can see the screen and they can see the presentation slide, which is up and running. Uh,
Yes,
Amritesh
fine,
sir
sir.
is, yeah, okay,
Fine. Yeah,
perfect.
continue.
So I'll move ahead. Okay. So thank you for joining me. So for this next 1 hour, we will discuss about the various test and measurement challenges which comes when we are working with wide bandgap devices such as gallium nitride or silicon carbide. As the topic states, the trends that are shaping a different power industry right now, that we see a lot of power industries. The way we work with different power industries, we have segregated into 5 different major power industries: industrial, automotive, data center, military, government, and the consumer electronics. And the recent trends that are being worked on the power industries are the power electronics, which is fast switching power converters, maybe AC DC or DC DC, power integrity, which we also call as digital power management, wideband semiconductor characterization system based on GaN and SiC, and the battery management system. So these are the 4 major topics which are the hottest trends in the power electronics industry that we see right now. We'll talk about the fast switching power converters. Basically, these are some of the application areas from the aerospace or defense, and some of the white papers which you can always go through in the automotive, aerospace, and defense, industrial, lighting, or consumer. We see a very much usage of GaN and the SiC based devices into these industries. Some of the market segmentation is given in such a manner that if you are working on lighting, then maybe from the light bulb, residential lighting, commercial or industrial lighting. If you're working on industry, then maybe into UPS, motor drives, or industrial power supplies, or in form of energy, consumer electronics, mobility, others in terms of aerospace and defense applications. So as you can see that power industry is everywhere, wherever we see a lot of application related to power in different domains. Talking about these, if you look at the overarching trend from the size and the power density, this is basically a battery charger which has been taken from SiC based device. So the motive is to shrink this charger and get a high efficiency of 80%. That's the main goal volume. And how do you achieve this size and power density? That's basically because of the semiconductors which are being used into this particular domain. Going forward, how do you get more power density? How do we understand the more power density part of it? So left hand side you would see a 200 volt silicon device of 30 milliohm radius on, and there is a 200 volt gallium nitride device which is 25 milliohm. If you look at the size of that particular 200 volt and 200 volt GaN device, there's a drastic change into the size. The same size, if you look into the solution as a chip and a complete device, then both the device based on the gallium nitride and silicon solution are completely two different. So small size, high efficiency. So you need to have high switching frequencies which are achieved through small parts, capacitor or inductors which are being used into the device. So we can conclude that wide band gap technology enables high power density. But this is not that simple. So there are a lot of challenges, there are a lot of differences which comes when it comes to GaN or SiC based devices. It's not directly related to SI. the way we work with SI. So how does GAN and SiC differ from SI designs? So that's major important. Miller charge is much lower, which allows fast switching speed. If you compare the GAN and SiC devices, the Miller charge of these devices are very lower, so you can have more fast switching speeds. Gallium nitride requires the maximum VGS voltage, and maximum VTH is much lower compared to SI devices. If we talk in terms of SiC, they require high VGS and negative bias on VGS, which is majorly an impact in terms of the GAN and SiC based devices. The body voltage drop is much higher in terms of the gallium nitride or the wide band gap devices. So they require very tight control of dead time to minimize losses. If we continue these differences, so regarding the device which are used in power applications, the main characteristics which are needs to be taken care, which are based into this table, are conduction efficiency, breakdown voltage, switching efficiency, the size and cost. So if you look at the band gap voltage itself, so from silicon it is 1.12, with respect to gallium nitride and SiC it's 3.4 and 3.32 eV. With respect to the breakdown electric field, it's too much higher than the silicon devices. With respect to the electron saturation velocity, it's much higher, it's almost double than the normal SI devices. Also in terms of the electron mobility is comparatively higher. So these are the main characteristics which comes with respect to Si and gallium nitride and SiC based material. So using the parameters above indicated, so it's very much possible to drive the theoretical values of RDS on the resistance values as a function of the breakdown voltage. In the below figure, we can very clearly identify that SiC and gallium nitride devices present a better relationship between the on resistance and the breakdown voltage, which is much value higher than a critical electric field. So the main advantage which comes from the use of these two materials consists of more compact package size. Moreover, gallium nitride, due to high mobility of the electrons, allow building power devices with minimal conduction losses. So the losses comparatively to silicon-based devices are very much lower than in gallium nitride with comparison to the silicon-based devices. So these are some of the major factors that comes with respect to these devices. How does this affect testing? So we all know that the recent trend that we see in the slide set, that the recent trend which is going into the gallium nitride and SiC, going forward, the industry is very much moving into the gallium nitride, and the testing setup, which has been the semiconductors which are used into the AC-DC or DC-DC converter, have become much critical when you wanted to use these devices, and the testing becomes a much bigger challenge. So how does this affect testing basically? So as we discussed, the critical parameters, Miller charge QG much lower, which allows fast switching speed. So you require significantly less parasitic capacitance in the measurement setup, less resistance and inductance that needs to be measured. So you should have a system to measure extremely fast dV by dt and di by dt, which are the fast slew rate, high frequency, and reduced loading, inductance, and capacitance. Another testing requirement is the threshold voltage is much lower, the high VGS. So we require a very tight regulation of VGS and VTH. So you should be able to measure VGS, the gate source voltage, on all gate nodes in a circuit on high side and the low side of a circuit. Body voltage drop is much higher. So ability to measure turn on, turn off, dead time, and eliminate measurement effect of phantom ringing on high side and the low side switches. So if you look at the critical parameter which are being required for the testing of GAN and SiC devices, we should have the right hand side three major capabilities into the system as a test system where we wanted to measure. You should be able to measure the dead time, which is the way critical method measurement when we comes to a switching of a particular device. You should be able to measure the turn on time. You should be able to measure the turn off time. You should be able to accurately measure the VGS on the high side and the low side simultaneously. You should be able to measure the extreme fast dV by dt and di by dt, which is very fast in nature. So if we summarize all these three parameters, then these are the three measurements which comes into the picture. Gate source voltage characterization on the low side and the high side. Dead time optimization. Dead time is obviously everyone, I assume most of the people knows about it, but if you are not aware, I'll go a little deeper into it. VGS characterization is one important. Dead time optimization, efficiency and loss analysis of the switching devices is another important parameter. So the measurement which are on with respect to the ground reference are very easy to be measured, but the measurement which are floating is are very critical measurement, and they are very difficult in terms of the new devices present into a system. So why dead time optimization is important? So if you look at these two pictures, on the left hand side there's a circuit which you show there's a 5 volt present. We need to measure in the presence of the 100 volt common mode voltage. So when one of the devices is turning on and another is turning off, we need to accurately measure what is the turn off the first device and what is the turn on of the second device. So the timing between those two parameters of turn off and turn on is basically the dead time, in which one device is turning on and the other device is turning off, or vice versa. So it's very, very important to measure that. Due to the lot of ringing effect, as you can see from the figure, due to the lot of ringing effect, the testing becomes a challenge, and the user does not have a control over the measurement in terms of the turn off and the turn on. So he generally takes a lot of margin when it comes to the measurement of the dead time optimization, taking an extra margin so that the system can work perfectly. But the switching speed goes on a toss when it takes over too much margin in respect of the turn on, the turn off. So dead time optimization is one of the key critical measurement when it comes to the basic measurement of these particular devices in terms of gallium nitride and SiC. Because of the lot of ringing effect, it becomes a challenge. Why does these ringing effect happens? So going forward, we will also talk about the lot of ringing issues that happen in these type of devices. How do you make these measurements? So basically, generally when people wanted to do a switching characteristics of any specific MOSFETs or any devices, they generally use a traditional high voltage differential probes. This is a very, very common method in the industry. Every one of the power electronics people uses high voltage differential probe. So I have few of the questions. Does it have the required bandwidth? First, does it have a required voltage ratings which are required for GaN and SiC? Does it have a required floating voltage ratings? Does it have a low enough inductance? Does it have a low enough capacitance not to load your circuit? So the answer goes very, very clearly no. Why? Because if you are talking on the gallium nitride devices, as we know that the devices are basically designed to be work with a higher switching speeds. So there are gallium nitride devices which can GaN devices which can go as high as 1 gigahertz. So the differential probes which are available in the industry right now, they don't have a required bandwidth, so they can't go up to 1 gigahertz. These devices are tend to be work in 600 volt and 1200 volt respectively if you're talking on gallium nitride or silicon carbide. So these devices, when you talk in terms of the GaN and the SiC, so the combination becomes 1 gigahertz 600 volt, or the combination become 200 megahertz 1000 volt. So the voltage ratings and the frequency ratings are much higher, which are not basically present in the differential probes. So that is one of the reasons that these differential probes are not compatible enough in the industry. There is no differential probe which is compatible enough to measure the exact switching characteristics of a particular GaN and the SiC based devices. So what really happens actually when we are using these type of probes? So this is an example taken from a MATLAB simulation of a device. So we have taken this picture from showing a Miller plateau of the device. So as you can see, when you run a simulation, this is the expectation. This is the gate VGS threshold voltage, and then we have a Miller plateau where there is a Miller charge, and the device get turned on at this particular stage. So this is an expectation that comes into a simulation when you do a simulation of a particular device. But this is not a true characteristics when the device goes actually into the DUT. The true characteristics look something very similar like this. So you will have, so as you can see in this purple waveform, the waveform is, you can't able to figure out where exactly the Miller plateau is settling down, where exactly the turn on device is settling down. So it becomes a very key critical challenge for the user to understand the turn on time of the particular device. So if the device turn on time is not characterized properly, then the device conduction time is not characterized, then the device turn off time is not properly analyzed, and the user will not have the margins to understand where exactly my device is turning on, where exactly my device is turning off, and where exactly how much time the conduction is happening. So it becomes a very, very challenge for the person who's actually working on the gallium nitride or the silicon carbide based device, that how exactly the device is operating in the turn on region or in the turn off region, how the high side is working, how the low side is working. Those becomes a very key critical challenge when it comes to the testing of these particular gallium nitride or the SiC based device. This happens because of the fast switching characteristics First of all, this happens because the device is, you require very, very low inductance and capacitance into the system to measure these. So the differential probes that you use in the industry are not capable of handling these situations at this particular voltage and the rise time levels. So that is why you get a lot of ringing effect into your measurement. So next time, whenever you see a lot of ringing when you are doing a gallium nitride testing, it might be because of the probes that you are using in order to characterize a switch. It might not be because of the noise that is coming into your device. Okay, so common mode rejection ratio can be very, very deceiving factor into this. Please make sure that you understand the values in terms of the common mode rejection ratio. What is the exact common mode rejection ratio at that particular frequency? So for 100 megahertz, we can see the common mode rejection ratio is greater 80 dB in terms of DC, or 60 dB when it hits 100 kilowatt. But when we are working on the gallium nitride and silicon carbide based devices, you need a better common mode rejection ratio, because if you wanted to do a low side and the high side measurement, common mode rejection ratio becomes a very, very critical factor, and this measurement value needs to be much, much higher. So how exactly the probes work behaves? So I have taken an example of a Tektronix THDP0200, a 200 megahertz probe, which is rated up to 1 kilovolt RMS. So if you look at the graph that is being indicated, differential red one. So at 1 kilovolt on the VRMS 1 kV, it tends to go at particular frequency which is somewhere close to 1 megahertz, and then it drops down drastically. And this is the physics which works beyond for every differential probe available in the market. So any differential probe that you see, the characteristic graph, so this is basically the frequency versus voltage graph of our differential probe. So this is very, very much similar, almost very common for all the probe, differential probe that happens to in the market. So now let's say if I use the same probe with a gallium nitride based device, which is rated to work at 600 volt and let's say 100 megahertz. So I know that 100 megahertz, it's not rated to work at 600 volt. So it drastically drops down. So you cannot characterize actual characteristics of the switch with the respect of this probe. And this happens with all of the probes. So this is an example which shows you the roll-off graph of a particular differential probe at 1 megahertz. So this is very, very, you don't get the full dynamic range at full bandwidth. This is one key critical difference that needs to be understood when we are trying to measure any gallium nitride or silicon carbide based devices. Another problem is the common mode problem, which I showed you an example that most probes have very, very poor CMR, which is above few megahertz. I have taken an example of this in terms of some numerical numbers. So we can see that this is 100 volt on the lower side and this is 105 volt. If you wanted to measure the difference between 105 and 100 volt, the differential voltage, which is approximately 5 volt, if you have a 20 dB loss, 20 dB common mode rejection ratio, then you get a 10 volt error. But if you have a higher dB value, then you get a 100 microvolt error. So it becomes very, very critical, very, very important to understand the common mode rejection ratio of the probe at particular specified frequency ranges. So this gives you an error percentage with respect to the probes and with respect to the measurement that is being taken care of. So how do we solve this problem? So yeah, so these are the probes that is available in the market. This is the problem that happens when we're trying to measure or test this system. How do we understand that? How do we get this problem solved out? First problem is, how do we design a probe for WBG testing? You increase the bandwidth. That is the first requirement of a differential probe. You increase the bandwidth. To drastically increase high frequency common mode response, CMMR ratio has to be improved. You need to reduce the ground loop inductance. So the one you see this circle of the wires, which creates a lot of ground loop, it has to be reduced. Second is fourth is you reduce the input capacitance. So you require a probe with a low inductance and low capacitance. You completely shield the signal at the board. So the signal which is need to be measured on the switches has to be shielded completely, so that you don't face a challenge in terms of the measurement. Okay. This is where we provide this ISO view, which is an optically isolated differential probe system, which is industry defined and the testing certified method, one of the certified method for WBG testing, which is an optically isolated differential probe system that needs to be understood when we're trying to measure the WBG devices. Okay. the basic characteristics, if you talk in terms of it, so this is one of the proprietary technology that really needs to be understand, which is working at 1.2.5 kV input range, 60 kilovolt CMR ratio, common mode. The frequency range goes up to 1 gigahertz, and the CMR ratio is 1 gigahertz is 80 dB. So the way we were seeing into a normal differential probe, it was 100 megahertz, and the common mode ratio was somewhere close to 25 dB. Now we are talking of 80 dB at 1 gigahertz. So we have increased the common mode CMR values and drastically with respect of the frequency ranges. And we could understand that high common mode rejection, high bandwidth, wide input flexibility, and the maximum flexibility gives you the maximum accurate result in terms of the measurements. This is where exactly the CMR ratio is defined. 1 million is to 1 at 100 megahertz. So now if you're planning to work on any of the GAN based device characterization or a SiC based device, this is one solution that really helps you to understand the complete characteristics of the switch in terms of the switching characteristics in terms of turn on, turn off, and the conduction losses. So more than 10,000 is to 1 at 1 gigahertz. Okay, so you can completely characterize your entire switch. You can characterize your gate voltages, VDS, and I current. You can characterize the time alignment of high and low side events, optimize and tune switching characteristics, which are the edge rates, overshoot, ringing, and the dead time. So now if you look at the different connectivity option, if you look at this particular graph, you would see the high side VGS, there is a very less ringing in comparison to the ringing that was seen earlier. So when we are using a proper ISO view probe, it becomes very easy and very accurate for the user to characterize the entire switch. So there are different connectivity options that comes into the picture. How would you connect your probes to your switch? So you might be connecting using wires, you might be connecting using different type of square pins, or you might be using different type of MMCX connectors. So when we are designing the GAN devices, when I'm working with different users who are working on the GAN devices, they generally prefer doing an MMCX connectors. So MMCX connectors are the most highest, best performance, high bandwidth connectors which are being used when we are trying to design the boards for the GAN or the SiC based systems. So it becomes very critical for the users to have the connectivity on their boards when they're trying to design any of the GAN or SiC based connectors. Okay. Obviously, does the scope matters? The on the as a tectonics, it's very important that you understand the characteristics in terms of the dead time optimization, in terms of the turn on, turn off characteristics. But there are few other critical measurements with respect to the power converters, which becomes very important to analyze. So these power converters are basically, if you look at the diagram, I have taken a diagram of a small AC-DC and a DC-DC converter working. So from the input side to output side to power stage and the control circuit, we have taken the different measurements setups at different places. So from the switching analysis, if you look at the switching losses, this is one of the key aspects. If you look from the real-time safe operating areas, dynamic on resistance, dead time optimization is one that I was talking, PWM signals measurements, from the amplitude analysis, from the magnetic analysis, if you wanted to characterize the inductors, the losses into inductors, the magnetic properties into the transformers or inductors, so the magnetic losses, magnetic properties, inductance, control loop analysis, if you wanted to do the complete stability performance characteristics of a converter. So right from the frequency response to power supply reaction ratio to line and load regulations to impedance measurement, right from the input analysis from power factors, harmonics, inrush current, input capacitance to output analysis in terms of ripple, switching ripples, efficiency, turn on time, turn off time, to the different type of compliance testing standard part of it. So These are, if you look at the breakdown of these measurements all together, so we have defined into the system, such as you can have the input analysis separately, you can have the output analysis separately, you can have the control loop analysis separately, you can have the transformer testing part of it, you can have the inductor analysis part of it, you can have the PWM analysis part of it. So the whole setup is defined in such a manner that you can have multiple testing in terms of the complete converter power electronic design testing can be done into a single platform. This is an important aspect. So if you look into the power quality, then obviously power quality is a very important parameter when we are trying to measure any of the based on the WVG devices or the normal silicon based device also. So they help to understand all the power quality parameters, right from frequency, VRMS, IRMS, VCF, ICF, or true power, reactive power, apparent power, power factor, phase angle. So this is another key important measurement. Another is the harmonics part of it. Okay, harmonics, everybody knows that, everybody does this harmonic analysis. This is very super important, one of the super important parameters when it comes to power electronics. So we have defined those harmonic standard as an inbuilt into our system, where the users can have the standard directly available from 61000-3-2 to AM14 to MIL 3099 to DO160. So these are the different standard depending upon the converter designed for what type of application. So if you are designing the converters for, let's say, for military applications on the shipboard, then obviously MIL 1399 harmonics analysis has to be done. If you are designing your converters which has to be used in the airborne standards, so DO160 is one key standard which needs to be taken care of. So it depends upon how do you want to correlate your harmonics into with respect to what particular standards. Inverse current input capacitance, this is obviously the one of the key important measurement that needs to be taken care in. How so if you wanted to design your input circuitry, protection circuitry, so you need to understand your inverse current, and the input capacitance measurement has to be taken care at that particular place. Okay, this I have already talked about when it comes to GAN and SIC or SI based devices. Switching loss measurement, where we understand the turn on losses, turn off losses, and the conduction losses. So you can actually analyze how your device is turned on, how your device is turning off, and what is the turn on time, what is the turn off time, what is the conduction time. So we can directly analyze all those values directly into the system. So it becomes a very easier for the user to completely characterize the switching system as in one complete setup. Switching analysis also gives you a values in terms of the dynamic RDS on, the dynamic on resistance. So this is also a key critical parameters. All these measurements are taken into a live setup. So these are not the in recorded or offline analysis. These are online analysis when your circuit is actually working. So if you go into whenever we buy any particular device for our design, so there are some specific parameters that are defined at a particular room temperature. So there are some of the parameters that might change when the temperature get changed. So when the device get actually into the circuit, and when we are actually operating that device on those particular with surrounded with different components, then the RDS on values tends to get changed. So these values are in live circuit measurements. So when the device is actually working into the design, so it becomes very useful for the users to understand the IDS on behavior with respect to a change in temperature. So this is a very key critical important measurement that helps the user to understand the dynamic resistance of that, but which helps to understand the conduction region of the devices. Safe operating area, this is another important measurement where the user can actually design the understand the safe operating conditions of a particular device. So the device is defined into three direction methods. So maximum current, maximum voltage, and maximum power. So as you can see from the graph, so similarly there can be a graph which can be designed into the system where you can see actually the device is failing into what region. Is it failing into the maximum voltage? Is it failing because of the maximum power, or is it failing because of the maximum current? So this is this is one of the important parameter that comes into picture. So it's very key critical measurement user needs to understand when they're designing their actual system from in terms of the safe operating area that needs to be defined. So when the device is operating into different conditions, into different load conditions, when the device is operating into different load conditions, it becomes user uh, importance to understand the device maximum load conditions in terms of the maximum current, maximum power, or the maximum voltage. Okay, another key measurement is the magnetic analysis. Most of the device, most of the conductor, most of the converters actually uses a lot of inductors, lot of transformers into their designs. How do you understand the magnetic analysis of those particular devices? If you have a transformer, what is the losses which are coming into the transformer? What are the, if you're having an inductor, what are the losses which are incurred into the inductor? So there's a very important characteristics of these devices, which is known as the BH curve analysis, which is the magnetic property. If you wanted to understand the inductance, what is the inductance of that particular device, what are the losses that are happening? So we define the losses in terms of the copper losses and the total magnetic losses, core losses and the copper losses. So the core losses can be defined from the transformers or the inductors from the data sheet. But how do you define the copper losses that are actually happening into the system? So there is a method to understand this. We can calculate the inductance, we can calculate the magnetic losses, we can calculate the magnetic property, which is B peak, BR, HC, H max, I delta B, delta H, and the permeability. So as you can see very clearly from the graph, we have an inductance curve, there is a BH curve, there is a saturation, I versus integral curve, there is a voltage and current signals, and then there is a measurement on the right hand side. It becomes very, so understand, try to correlate with your design circuit that you are already been working on. If you are working on any of a AC DC or let's say DC DC converter, so you might have some input stage, you might have some switches, you might have some transformers to step down or step up, you might have some output signal. So if you are characterizing an input side, which you already did into the earlier slide, if you are characterizing on the the switching side, the way we did the switching analysis, now it comes with a transformer. So it becomes a whole system approach to understand the complete power electronics measurement that comes into a single platform, and you can actually analyze those systems in a single platform. Okay. Another is ripple. Ripple is very, very important. Obviously, ripple is one of the key important parameters of the converters. So if you're designing any AC DC or DC DC converters, it becomes very key critical measurement. Now the ripple is not only of ripple is basically characterized into two different type of ripples. There can be high frequency ripple, there can be low frequency ripple. Now let us just take an example. I'll talk an example. If you have a DC DC converter and you have an output ripple that is being measured as 10 millivolt, let's say for that matter, but we can put some filters at the output side and we can eliminate that particular portion of the ripple and we can bring it down. But if you wanted to go into the root cause of actual ripple, where it is coming from, is it coming from the switching frequency, switching components, is it coming from the line ripple, which is 50 hertz line power, which is working on? So we have defined a system in such a manner that we can segregate the ripple in two different formats. You can segregate the ripple based on the frequency. So if it is because of the 40 kilohertz MOSFET ripple coming in, or is it because of the 50 hertz line power ripple coming in? That is why we have defined the ripple components as the low frequency ripple and the high frequency ripple. It becomes a very easier method to understand the exact ripple to come measure into the whole system. Okay, power efficiency. Power efficiency is another key important parameter. If you wanted to analyze the complete efficiency of the whole system, then power efficiency is none other than less. It's an easier method to analyze and to understand the importance of these particular system efficiency at the same platform. Okay, this is a lot of power electronics people generally don't talk about this, but yes, people have been doing it, people prefer doing it, and they have a challenge of doing it. So this is basically the control loop response or the Bode plot capability. How exactly the Bode plot is basically the stability of the complete converter, how your converter is going to behave with different load conditions. So that's one of the important measurements. So control loop analysis gives you the regulation characteristics of your power management circuit. The compensation network should be optimized in order to meet the static and dynamic performance. So these are some of the important parameters. That's why people do these control loop response. They generally test the crossover frequency. They generally test the gain margin and the phase margin. Okay. So this is the control loop response measurement that is very critical. Another is the power supply rejection ratio. So if you are working on the DC-DC converters or if you are working on any of these devices which basically perform these type of tests. So how do you understand the power supply reaction ratio of these devices? How do we understand the characteristics of a DC-DC converter? So it becomes a key critical measurement when it comes to a DC-DC converter analysis. So in order to perform a power supply reaction ratio test, a sine wave must be injected at the DC input, and we sweep that from a low frequency to a high frequency, and then we calculate the complete system of a power supply and then analyze the whole system directly into the same platform. That's where you understand the kind of power supply reaction ratio measurement. So how do we plot this with Tektronix? So Tektronix has a very easier method to analyze the Bode plots or the power supply reaction ratio, where you can calculate the gain margin, you can calculate the phase margin. So as you can see from the slide set, you can calculate the gain margin response, which is coming as showing with respect to dB in terms of the frequency, also with the frequency correlation. If you wanted to have a phase margin, then you can also calculate the phase margin percent degree with respect to the frequency ranges. So a very easier setup that helps you to understand the Bode plot. Okay, key important measurement is impedance measurement. So how do you do the, so everybody knows the reverse recovery current that really happens when you are designing a DC-DC converter. So if you wanted to do an input impedance measurements, how do you do it? So you want to measure their PDN impedance and make changes in the design to ensure impedance mismatch is removed from the design, from the converter. In other words, how much LCR values are optimized. So that's basically the measurement on the impedance side that is being done, and you calculate the impedance profiling of the complete converter. So that's one of the key critical measurement. Okay, coming to the SiC and GaN power converter analysis kit. This is exactly, we have a full setup of the SiC and GaN converter. So you can do all your switching characteristics, you can do all your uh, input characteristics, transformer characteristics, magnetic analysis, output analysis, ripple characteristics. All of that can be done into a single platform. Tektronix has some dedicated tools related to hardware and software that can help you to understand all of these uh, applications were much easier to analyze into a single platform. Okay, so if you wanted to recap in a nutshell, so fast switching, we require high bandwidth of the probes. Fast floating differential measurement require very high CMR ratio. Instrument always influence measurement solution. Accurate measurement rely on suitable instrument for that specific measurement. Okay, so thank you so much. This is from the presentation slide, but I would also want to show you some of the live actual hardware which has been connected at my setup, and wanted to show you some of the live GaN based device measurement just to show you. I'll just switch it off and then move it to the actual system. Okay. So, Amritesh, is it visible?
Yes, sir. It's fine.
Okay, perfect. Okay. So for the users who are there with us, the listeners, I have connected a Tektronix MSO58, which is a mixed signal oscilloscope, to my laptop using a LAN cable. So this is the instrument which has been connected. This is exactly where we see the instrument control. We click on this and we get onto the control of the instrument. Going back to the slide set, I'll just show you before I get into that. Okay, I'll explain you. This is the actual setup which I'm trying to do. So I have connected a device which is a gallium nitride based device, which is a GaN demo setup. So we have a VGS high side, VDS high side, VGS low side, VDS low side, and a shunt current. So this is actually the setup which is being connected. I'll just show you the Miller plateau part of it, so that you can exactly see how Miller plateau is being characterized into the system. I'll also show you some of the key important parameters measurement related to the power converters, from the input output to the switching to the magnetics, all of it, so that you can at least have a feel on exactly how is it happening. Okay. Okay. So showing you the one of the key examples, channel 1, I have connected a normal probe, which is an 100 megahertz THDP probe. On channel 2, I have connected a specialized ISOView probe, which is an optically isolated probe. On this is the system is being connected onto the VGS side. So if you look at the channel 1 and the channel 2 characteristics, in terms, this is exactly, they both looks very similar. If you look at the pulses look very, very similar. But if you go detail into the exact Miller plateau, if you wanted to exactly see how the device is being charged at the VGS side, how exactly we are seeing the Miller plateau portion of it, we need to go a little zoomer into this particular measurement. Yeah. Okay. So now you can see channel 1, which is the yellow, and the channel 2, which is blue. We can very clearly identify there is a particular glitch which is happening into the channel 1, but in channel 2, the device, you can see a very stable platform in terms of the Miller section. So I'll just zoom it a little more. Okay. Use some cursors. Okay. So we can clearly see this particular area between cursors on channel 2 delta. Okay. This is exactly 2.2 nanosecond. So this is the 450 megahertz Miller frequency at that particular range which we are seeing into that. So 2.2 nanosecond Miller charge is there, which is not able to be sustained or which cannot be measured onto a differential probe. If you look at the channel number 1, okay, it's not possible. It's definitely not possible. You will not be able to see. Let me just switch off the cursors. Yeah, so you'll not be able to see this particular. I'll overlap these two. Yeah. Yeah. See, so how what is the, so now what is the problem? So going back to a slide set that we referred, if you if you are doing this measurement, let's say, it becomes very easier to understand where the device is actually turning on. But in terms of the channel number 1, which is being done onto the differential probe, it becomes very, very wrong measurement, I would say. It becomes very unimportant, or you cannot do a correct measurement on channel number 1. It becomes tough for a user to understand the turn on characteristics of this device. Similarly, if the device has been connected, so this is on the high side. If I would have connected, if you go on to the lower falling edge, you'll be able to see very clearly, okay, the exact differences that happens onto the falling edge also. So yeah, so look at this falling edge. So it becomes very tough for the user to understand where the device is actually turning off. So turn on time, turn off time characteristics. So unless until the user is able to characterize the correct switch, turn on and turn off, and the conduction time, he'll not be able to do a complete margin testing in terms of the dead time, in terms of the conduction losses, in terms of the switching losses, in terms of the uh, complete switch characterization feature. So this is one of the key example that you can just correlate with your measurement. So lot of ringing. So the ringing which I was talking about was this particular ringing that is happening in the yellow channel, the channel number 1. But if you look at the channel number 2, the Miller plateau is very, very clearly visible. So now if I had to compare this results, I'll just pull up that particular slide. Yeah. So now you can compare this result with channel number 2, the blue one. So it becomes very easier for user to identify. Okay. So this is so measurement result does not match the expected result. This was the idea of so that is why Tectonics have come up with an isolated channel probe for this particular type of measurements. Okay. Yeah, I hope this particular example makes a lot of sense when it comes to the gallium nitride or SiC based devices. So if you wanted to do a rise time measurement of these devices, let's say measure rise time of channel number 2. Okay, so it's 5.5 nanosecond if you wanted to measure the rise time of channel number 1. So yeah, so just imagine from 5.5 nanosecond, it is coming close to some random values. You are not even getting some good values. But in terms of the channel number 2 measurement, the measurement is very, very clear, which is 5.1 nanosecond. So it becomes very easy for the users to do these type of measurements. This is related to the switching characteristics of the GAN devices. I'll just turn on some few other measurement for your live measurement for your reference, which will give you more broader idea on exactly how these measurements are taken care on a different type of power. Yeah, I'll just connect it and then I'll show you some other live measurements. Okay, so now what I have done, I have connected a voltage probe basically and a current probe on a converter. Okay. So these are the one voltage and one current signal that you can see on the screen right now. Okay. Okay. So yes, I have connected a very very noisy current channel intentionally so that you can actually see what type of losses happens when we are doing the measurement on the current side. Yeah. Yeah. So this is you have measure, you go to power, you have this dedicated tool where we can see the power quality. Take it directly a power quality. So we can on the right hand side we can see the power quality in terms of the frequency, VRMS, IRMS, all those particular power related measurement. Okay. We also have this in power quality. We have this harmonics where you can see the harmonic count with respect to this particular bar graph, and this measurement can also be analyzed. You can see the bar graphs of various measurement into the system. So it becomes very easier for the user to analyze. So I'll just be a little more specific. Yeah. So you can see the F magnitude, F3 magnitude, THD fundamentals, THD reference, RMS values, and the frequency. You can see the blue as the fundamental frequency and the respective frequency ranges as the green harmonics chart. Definitely, the user can set their harmonics of the source. They can select the voltage or the current source. They can select the line frequency, 50 hertz, 60 hertz, 65 hertz. So you can do a custom frequency range also. It becomes very easier for the user to analyze the analysis of these particular setups. So in measure, directly going to power, doing the harmonics, power harmonics, inrush current, input capacitance. Coming to the switching analysis, we have the switching analysis directly. So let's say if I want to do a switching loss, so I'll just pull up the switching loss. So on the right hand side, you'll see the turn on, turn off, and the conduction losses. So T on is 890 milliwatt somewhere, T off, and then conduction loss, and the total loss is 1.4 watt. So this is a direct measurement in terms of the switching loss characteristics. So we have a different methods to calculate. We have SMPS, we power factor PFC flyback topologies. Then we also have the gate voltage option. We can do RDS on values. We can do a BJT, IGBT. So all these measurements can be directly done, and they can be exactly calculated the switching characteristics. When we go in terms of the gallium nitride or SiC based designs, the characteristic that's more important to analyze is with respect to the probes. So the probes play a lot of major factor when we are doing the characterization of the GAN or the SiC based device systems. Okay. Similarly, you can go to measure, and we also have these magnetic properties. So magnetic analysis. So let me just pull out this power quality for a time being, and then okay, so you go to measure, go to power, and then pull up the magnetic analysis. So magnetic analysis help you to understand the magnetic property of your transformers and the inductors. Now there are a lot of questions that there are a lot of mechanical properties related to a transformers. Let's say the number of turns, the primary turns, the secondary turns. How do you take care of it? When we pull up the magnetic property, then in that we have multiple options where you can configure that physical properties of the transformer. You can set the voltage source, you can set the cross section area of the core, you can set the magnetic length, you can set the primary turns, you can set the number of transformer secondary turns. And on the right hand side you will have a very clear indication of the magnetic property. You can see the values that are being calculated on the right hand side, exact right side bottom, B peak, BR, B max. So you can exactly see how your transformer is behaving in the real life conditions. So when the transformer is actually into the DUT, when you are operating into different temperature ranges, when you are operating with different voltage current ranges, how your magnetic property is being characterized, it becomes very easier. Similarly, you can also plot, go to magnetic properties, and you can see the magnetic losses. So it becomes very easier. So directly we can calculate the magnetic losses. So 638 milliwatt, that's how it's being calculated of this particular transformer. So directly calculating the magnetic losses. Another important is the ripple. So we have this line ripple, switching ripple, efficiency. So as I was being discussing, when we go to switching ripple, we just calculate the switching ripple and we calculate, configure it with respect to the frequency. So if your switching frequency is 40 kilohertz, uh, uh, with respect to the switching frequency, you can set this frequency, let's say for 40 kilohertz, and then you can measure that. Okay. 40 kilohertz, enter. So the switching frequency is 40 kilohertz, and then the ripple will be calculated based on that. If you are doing the measurement in terms of the line ripple, so you can directly calculate line ripple, pull the line ripple measurement, okay, and then configure it as per the different line frequencies. So 50 hertz, 60 hertz, any of this. Okay, coming to the another measurement that we discussed was with respect to the frequency response analysis. This is the control loop response. So you can see a control loop response, the power impedance profiling, and all of these measurements are directly being taken care into it. So the system is being designed to work on a 12-bit system. So you get the highest accuracy in terms of resolution. So from directly converting measurement in terms of the GAN and SIC, or measurement in terms of the power converters, you can do an end-to-end solution that can be analyzed into the same platform. Just to show you a very good example of how exactly the power measurement, if you're doing a magnetic measurement. So this is a very nice example that demonstrate all of the uh, measurement with respect to the magnetic. So R1, R2 are the waveform, the voltage and current, and then this is the BH curve, and then simultaneously you get all of these measurement on top of it. So this is this is a direct measurement setup that can be analyzed. You can directly calculate the magnetic losses. So Tectonics helps power electronics engineers and design validation engineers and the designers to have the maximum quick approach toward the measurement setup that we do with our systems with respect to the respective softwares and the hardwares which are required for the gallium nitride and SiC based characterizations. Okay. So you can also do this particular. We have also launched a recent setup which is used for the motor drives. You can actually see the motor drive characteristics also. So if you wanted to characterize the three-phase motors with respect to the power quality and the phasor diagrams, so Tectonics has developed a setup which can do a three-phase motor drive analysis in terms of the uh, different type of DC AC or AC DC converters on the three phase. You can directly see the three phase measurement in terms of the phasor diagrams. So all the power related measurement, right from the converter drives based on the gallium nitride or normal silicon based devices, right up to the proper three phase measurement in terms of the motor. Tectonics has worked all these different domains and bring all the and the related hardware tools into their setups when coming back to the whole setup in the measurement system into one particular platform. So with that, I'll just conclude my presentation with this. And if anybody wants to keep in touch, I'm there on LinkedIn. You can connect me with the name of Nitin Nigam. I'm also connected on emails. We can directly contact us or for more discussion on power electronics related measurement. So looking into a time frame, I'll end up my presentation over here. And thank you so much, NIT Silchar, Amritesh sir, and the coordinators for inviting us for this particular session. Thank you.
Thank you, sir. Thank you, sir, for such an informative session. Okay, so dear participants, actually, last day only, sir, that there's one person expert from Australia, Rebel Islam, and one person from ILC Bangalore, Runat Garla, sir, told you about the that's three important aspects for your power electronics. One was your design, modeling, simulation. Okay, and for all those things, you like whatever you design, whatever hardware you develop, how will you measure actually? You can't you measure just simply by use your multimeter or you require because you are really switching at very high frequency, so it requires accurate measurement. Okay, so this this type of the probes and measurements we require actually for particularly if you are dealing with your high switching frequency. Okay, so thank you, Nitin sir, for such a informative thing about the measurement issues. Okay, so actually, Nitin sir, there are some questions. I just
Yeah.
they are lying in the chat box. You can see
Okay.
participants have asked, so you may take few if you can, sir.
Yeah. Yeah. Sure. Sure. Sir. I
You can see the chat box,
okay.
sir. I already pasted.
Okay. So, what is significant graph between RDS and breakdown voltage? So you are talking on the slide number 10. Okay, so the slide number 10 graph is basically that particular graph is being derived from the uh, basic parameters of the GAN character MOSFETs. So the conduction efficiency, breakdown voltage, switching efficiency. So the main idea of putting up that graph is we can immediately observe how SiC and GAN devices, they present a better relationship between the on resistance and the breakdown voltage, determined by the higher value of critical electric field strength. The main advantage driving from these materials is basically the high mobility of the electrons, which show the allows building power blocks with minimum conduction losses. So that graph is basically shows you the relationship between the breakdown voltage and the on resistance, so that we can exactly see how exactly the conduction losses are less. So in order to understand the conduction losses of those GAN and SiC based devices, that was the main significance of putting up that graph. What is the problem with the GAN device current measurement except the source inductance of wire? Uh, Current measurement in the GAN devices is a very critical component to measure, because due to the probing technique that requires to measure the GAN device current, it's very, very low. So the ground loops which are being used into the current probes creates a lot of ringing effects. Yes, you are right, except the source of inductance of wire. So we are using the optically isolated probe in order to remove those type of inductance of the wire. So removing that uh, extra inductance of wire, the electrical wire which is used with the normal current probe, we are using an optical method, so the signal does not create any ground loops. What advantage can these devices have for applications in inverters? These are fast switching devices, so these devices you'll have a faster output in comparison to the SiC. The breakdown voltage is comparatively higher. The threshold voltage is comparatively lower. So fast switching, the size of these devices will be comparatively smaller. So low cost, low size, and fast switching devices, that comes as an advantage for the GAN devices. Most of the devices, IGBT and MOSFET was the main advantage. Yeah. What about the driver circuit needed for WB circuit? Do these measuring instrument will these measuring instrument will not help you in the driver circuit minimization, sir, as such, because these are basically the test and measurement devices. So when the device is being actually designed, you will put up these devices to use the characterization of those WBC devices. So that driver circuit minimization has to be taken care by the designer. Uh, the source meter question, I'm not sure exactly. Okay. Can brief as a demonstrated setup. So demonstrated setup what with me is a EPC gallium nitride board from EPC components, EPC circuits. So EPC is basically a US based organization which makes gallium nitride board. So I have a gallium nitride board which run on 1 gigahertz. That was the demo setup for ISO for the GAN devices. For other characteristics, which I was showing you, the switching losses and transformer losses and all those power harmonics. So that's basically I have an AC/DC converter on which I have connected multiple probes on the input side, transformer side, MOSFET side, and then I was pulling up the measurement which are automated into the oscilloscope to show you these particular measurement which we discussed. Okay.
Okay. Thank you. Sir, one question from my side.
Yes, sir.
Like
Please.
that we are saying that basically if we are using GAN devices and SIG devices, suppose for only 50 kilohertz or like 100 kilohertz, 150 kilohertz. So do we require to have a like a basic, what is the thumb rule for selecting the proper voltage probe bandwidth? If suppose my switching frequency requirement is 100 kilohertz, then what should be the bandwidth that we require for a voltage probe?
So generally when you talk, if your switching frequency is 100 kilohertz, sir, that is basically the switching frequency. We also need to understand the rise time of that particular signal. So it's not
Mhm.
only about the frequency; it's also about the rise time of that signal. If the rise time, let's say your switching frequency is 100 kilohertz, but your rise time is 2 nanoseconds, so then
Mhm.
the probe will be chosen in order to the 3 times better than the rise time. So a convention, like let's say if you're doing on 100 kilohertz, your probe common mode direction ratio should be mentioned at 1 megahertz, typically
Okay. Okay.
5 to 7 times. But when it comes to rise time, your rise time should be 3 times better than the signal rise time.
Okay. Okay.
So
Okay.
thumb rule is
Thank you.
three times. So
3 times.
summarize it 3 to 5 times.
Okay. Okay.
Yeah.
Thank you. Okay. So
Thank you. Yeah.
thank you, sir. Okay.
Thank you so much,
So
sir.
thank you. Thank you. Thanks a lot. It
And
was a wonderful session, sir.
just to add in, looking at the time frame, I have tried to cover and minimize a lot of things into one presentation. But if
Yeah.
somebody wants to feel and get connected on to more discussions, we have a team in US from Tektronix who has been actively involved with EPC and GAN systems. We are working very closely with them. We are developing new products related to softwares and hardwares with them. If you somebody wants to feel, get connected to me through so that we can get connected onto the design issues or the challenges. We have a team which is doing a lot of voice of customers globally. We have I am a part of that team who is working in India. Then we have similar team in China, Europe, America, US, basically who are doing the voice of customers. So if somebody wants to feel have a more discussion on the GAN specific test setups, so we can have one-on-one discussions. I have been involved with IIT BHU, IIT Kanpur, IIT Delhi, ISC Bangalore. So we are working with them in to understand their requirements and develop products accordingly. So if you have any specific needs with respect to those, please get in touch with me. I have my email ID mentioned. I don't know if I mentioned into my presentation, but yeah, this is my LinkedIn account. I'll just put up my uh, email ID for your reference. So you can just get in touch with me. It's nitin.nigam@tectonic.com. We can we can get more in detail with respect to the GAN device or the switching device characterization of or any of your power semiconductors characterization for that matter. Thank you.
Thank you, sir. Thank you. Thanks a lot, sir, for taking out your time for such a nice demonstration. Okay, so definitely the participants gets benefited, and you have given the like a solution and answer for most of the questions that has been raised. So thank you, sir, once again from United Silshire behalf and behalf of coordinator. Thank you a lot, sir, for giving a nice full presentation, nice full talk on this session, sir. Okay,
Thank you,
thank
sir.
you, sir. Thank you, sir.
Have a good day.
So
Yeah. Bye.
have a good day. So, dear participants, so that's all for today's session. Tomorrow again we'll start for the third day. So third day it's going to will start at 10:15 again. So first session tomorrow will be taken by Professor Venkatesh Perumal from NIT Surathkal. He will be dealing with control of grid connected PV inverter. And the second like your that second session in the third day that was supposed to take taken by Dr. P. Sanjeevi Kumar from Aalborg University, Denmark, but because of some preoccupied some job, he just like tomorrow this session will be taken by the this Dr. Nalin Bihari Dev Chaudhary and Dr. Asa Madam. That was scheduled on 10th actually. So that has been interchanged actually. So that is ninth session, that is the second session, had to be interchanged with the 10th session 2. Okay, so that's Dr. P. Sanjeev Kumar will be taking the session on polytronics in EVs and renewable on 10th, and the ninth it will be taken by the Dr. Nalin Bihar Chaudhary and Dr. Asarani. So there's a small change in the like the sessions. Okay, so and the afternoon session will be taken by again the industry person, Mr. A. Aziz from CDAC Trivandrum. He will be dealing with high-speed reconfigurable powertronics controllers. So links are already being shared in the YouTube, and it will be also shared in the WhatsApp, and also the links are being sent in the mail. Also, you can refer as per your convenience. So that is all about the session. We'll meet tomorrow in the morning. Have a good day. Jai Hind.